Welcome to the Elements of Deep Sea Mining. I'm Eric Young. Joining me today is Dr. Rahul Sharma, retired chief scientist from the CSIR National Institute of Oceanography in Goa, India. More than 40 years in the field of deep sea minerals. Rahul has a master's degree in geology and a doctorate in marine science. Dr. Sharma has published 38 papers, 41 technical reports, as well as editing special issues of journals and books, including Deep Sea Mining, Environmental Issues of Deep Sea Mining, Perspectives on Deep Sea Mining and the Water Column, and Deep Sea Mining Policy and Regulations. Rahul, thanks so much for joining me today.
Well, thank you so much for that introduction, and I'm happy to be here.
I'm really grateful that you made the time. I think people will recognize you as the person who has kind of literally written the book, or at least edited the book on deep sea mining. So maybe you could just start off with your background. How did you get into deep sea mining? I'm really interested to hear about what the field of deep sea mining looked like when you started into it.
Oh, yeah, that's right. In fact, it was soon after my master's that I landed up with this prestigious institute in India called the National Institute of Oceanography, which was just initiating a new program on deep sea minerals exploration. And since then, until my retirement in 2017, I've been associated with deep sea minerals. So you can say that I just landed up this job and something that was going to change the future. That's what I think. And I have seen it evolve over these 3 or 4 decades, which I can share with you today.
Yeah, please. Yeah. Give us some insight into what the field, especially in India, looked like when you got into it, and how you see it's changed.
Right. So India had been traditionally looking at the coastal mineral deposits, which are called the placers, the ilmenites and the monazite and semi-precious stones, etc., for many years before 1980. It was around the 1980s that probably the people who were the think tanks in the Ministry of Science and Technology and oceanography related subjects, that they realized that India, being an industrially developing country, needed more resources other than what we got on the coast. And the potential of deep sea minerals having such metals that could be useful in future had set in by that time all around the world. And that is when, around 1981, that India actually launched its polymetallic nodules program in the Central Indian Ocean, which is the largest basin containing these minerals in the Indian Ocean. And since I joined in 1982, so I was automatically inducted into that program. But then, having said that, India has diversified a lot since then, from traditionally used small boats for coastal placer mineral exploration into high-tech state-of-the-art technology that we started using, that was available at that time, including ships from countries like Norway and Finland and UK and all other countries, with state-of-the-art equipment, which we were exposed to at that time, which the government of India at that time thought that it would be something really useful for the country. That is what inducted us. Rather, it was a large group of about 60, 70 youngsters who were pushed into these ships every 45 days, off and on, continuously for a period of 7 years. So each one of us would have put more than 1,000 days at sea in those 6-7 years when the program started in 1982 officially. And by 1987, India had got its the area allotted in the Indian Ocean under the then preparatory commission of the UNCLOS, which was 150,000 square kilometers in the central Indian Ocean. So I can say that in India, we were the pioneers uh, for looking at deep sea minerals and identifying such areas that India could eventually claim. And that is what India has as the polymetallic nodules site in the Indian Ocean.
Yeah. Okay. So India, being in its position in the 80s as a developing and very large and very populous state, realized that it could use more natural resources, obviously. And you're saying that there was this awareness that there was potentially polymetallic nodules. And did it have to do with kind of the proximity, that there was some knowledge that there was a fair likelihood of these nodules in the Indian Ocean? And when you say that you spent so much time at sea doing cruises on and off for 7 years, was that just really exploration at that point and finding out kind of what was actually there? Like, how much information did you have going into this? How much knowledge of the resources was there? And yeah, how did that get filled in?
Right. So at that time, there were a few papers available from specialists who had made chance discoveries. I mean, it was not an intentional one to look at the polymetallic nodules, but then since it was known by that time under what conditions polymetallic nodules did exist, people started looking for these in all the oceans around the world. And so we had a few publications that were available at that time. Professor Cronin is a very big name in this, who belongs to the UK, and he is one of the pioneers. And his book came out in 1980, where he actually designated such basins around the world. And that was, I think, probably the starting point for us to look at the central Indian Ocean, which is the largest basin in the Indian Ocean. And in terms of proximity, we can say yes, because that was the closest one having the highest potential from whatever data was available at that time. And but then I would say that those were just chance discoveries that people had made at that time. But then published data was available, very scanty one, which we then converted into an exploration program of looking at something like 4 million square kilometers of an area to actually narrow down to 150,000 square kilometers, which eventually India applied for and got under the UNCLOS. So you can imagine narrowing down from 4 million to 150,000 square kilometers, how much work would have gone into, and that is why we had some about 100 expeditions and 1,000 days at sea, each person spending time out at sea, which eventually led to the identification of this site.
Yeah, to be honest, I really can't imagine what that would be like, trying to map out that that size of an area.
Yeah, so that was something like going blind with a couple of data points in such a large area, and then starting the surveys at 1 degree interval, which is about 110 kilometers apart at sea, and then plotting those data points in terms of abundances and grades, then narrowing down to half a degree, then quarter of a degree, and 1/8 of a degree into the potential areas that we thought were the most interesting ones. So it was actually looking for a small piece of land in a very huge, expansive area. But then we had to narrow down with a smaller grid in progression.
And maybe just tell the listener a bit more about the geology and what's out there in the Indian Ocean. So first of all, is it just nodules that are mainly of interest, or is there sulfides and crusts also?
Yeah, okay. So in the Indian program started with polymetallic nodules, which at that time was considered as the most potential, and probably today also, because of the comparative ease of mining, in the sense that the nodules are spread loosely on the ocean floor and they can be picked up like potatoes with a huge vacuum cleaner kind of a machine. So we did start with the polymetallic nodules at that time for that reason. But then eventually now India has two sites for polymetallic sulfides also, or hydrothermal sulfides, to itself under the Seabed Authority contract in the Indian Ocean. So now India has three sites in all, two for the hydrothermal sulfides and one for the polymetallic nodules.
And so when I was trying to educate myself on the minerals in the Indian Ocean, I saw that there's nodules located at the spreading ridges. And this to me seems a little bit different than what I think a lot of people have come to expect, is that nodules are in the kind of abyssal plains and the sulfides are connected to the ridges and the more active areas. I wonder if you can just clarify that for me.
So geologically, each basin that is there in the Indian Ocean and generally all around all the oceans is restricted between two major tectonic features. Similar is the situation for the Central Indian Ocean, where the Indian site exists. It is between the 90 East Ridge and the Central Indian Ocean Ridge, 90 East on the eastern side and Central Indian Ridge on the western side. The 90 East Ridge is not an active ridge, but the Central Indian Ridge on the western side is active in a sense. But then the nodules that we have found and we are looking at are not on the ridges, are not on the spreading ridges. They are within those abyssal plains, which are comparatively very stable areas. The deep sea plains, because the ridges are about, the top of the ridge would be about 3,000 meters underwater, whereas the nodule area is 5,000 meters plus depths. And these are flat abyssal plains on which these nodules have formed. But then, yes, bounded on both sides by tectonic features, the 90 East Ridge and the Central Indian Ridge. But then these basins do have their own set of geological features, such as small abyssal hills as well as seamounts. So small abyssal hills is less than 1,000 meter height. Seamounts is more than 1,000 meters height. And that kind of undulating topography also is responsible for the concentration of nodules within the basin. For example, the flanks or the slopes of these abyssal hills and the seamounts are the locations where there are higher quantity of nodules available as compared to the deep abyssal plains, which have higher sedimentation. So even if there are nodules, they would be buried under the sediments where they are more exposed on. So then, yes, you're right. Geologically, the concentration, or I would say abundance, of nodules is influenced by the local geological features such as abyssal hills and seamounts.
Yeah, that's interesting. I haven't pictured that before, that the nodules will be on the slopes of the seamounts. But that makes sense when you say that it's connected to the sedimentation, and that on the exposed slopes there's going to be less sedimentation kind of settling there. What about in terms of other comparisons? I'm just assuming that most of the audience is more familiar with kind of CCZ nodule situations. What about the mineralization of the nodules? Is it the same minerals in the Indian Ocean, or are there differences?
Of course, the Clarion-Clipperton zone, fracture zone within the Central Pacific Ocean, is again bounded by two geologically important tectonic features, that is the fracture zones. There is one fracture zone in the north, one in the south, just as the basin that I described in the Indian Ocean. So, but then these are the CCZ nodules are definitely richer in terms of metals, although the metals that we are looking at are the same. That is
Okay.
manganese, iron, copper, cobalt, nickel. Iron and manganese are not critical as far as the current research is concerned from mining point of view, but then copper, nickel, and cobalt, and the other rare earths that are found are the metals are similar, concentrations vary between the Pacific Ocean and the Indian Ocean, and yes, from what we know until now, Indian Ocean nodules are not as rich in these metals as the Pacific Ocean ones.
Interesting. Can you just, from a geology kind of formation perspective, is the proximity to these spreading zones, is that important for where the minerals kind of come from that make the nodules? Like, is the fact that there's such richness in these certain basins because the minerals are somehow coming out of the tectonic activity at the edges of the plates and kind of creating the background features for the mineralization? Does that question make sense?
Yeah, that's right. In fact, the source of metals in the nodules are the local sources. So, in geological terms, they could be either diagenetic or hydrogenetic. Now, diagenetic is something that comes, the metals that are leached out from the indigenous rocks or in situ rocks found in that area. So the leaching of rocks gives out those metals into the water column, which are absorbed by oxidation process into the nodular form. But then there are known to be hydrogenetic inputs also of the metal. And the hydrogenetic is something that has come from the water column. Now, from the water column could be again two sources. One, the dissolution of the shells of different organisms, which also contain certain metals. The shells that the organisms form around their body or within their body, when they dissolve, that also precipitates certain elements, which goes down the water column and gets oxidized around a nucleus forming, which hydrogenetic input is also one more source. The third possibility is volcanic source now, or volcanogenic, which is derived from those gases or leak fluids which are emanating from the geologically or tectonically active zones, such as the mid-oceanic ridges or the subduction zones. So that possibility is there, and it depends on the composition and the metal content that identifies what source it is made from.
Wow, that's clear and helpful. I've actually asked that question to a number of different people, and so I'm happy to get such a explicit answer. I guess before we get too far away from your background and your experience, so you've also worked in Japan and Saudi Arabia and on other international missions, and so I'd be interested to hear kind of what you're doing in those missions, but also your opinion on how the conception of deep sea mining differs nationally, if India has a different perception of it than Saudi Arabia, for example, and how you see that.
Yeah. So the perception varies between countries depending, one, on the level of development in research that they have carried out until then. This is what I found. I mean, there is a vast difference between what Japan is looking for and what Saudi Arabia is looking for. So Japan has the latest technology and the best things, and they can go to any depth and find anything that they want. So they are sort of pioneers in the Asian context in exploration and looking for minerals. So they are looking for everything. They have the best submersibles and they have the best equipment that can be. So they are looking at everything, right from polymetallic nodules to what they call as hydrothermal sediments formed by different hydrothermal processes, which they have found in an area called Minami Torishima Trench or something like that, uh, in the northeastern Pacific. So Japan is looking at these exotic minerals, I would say, which have not been either known earlier or which can be exploited for their industrial purposes. I mean, these are two contrasting examples that we are taking, whereas Saudi Arabia has been until now strictly looking at the Red Sea muds, which is the closest to its shores. So Red Sea muds again are rich in different metals that we are talking about, not only those which are found in the nodules and the sulfides, but some more. So Saudi Arabia has been looking for that. The interest of these countries would vary. Again, some would mainly be thinking about utilizing these for their own consumption because they have the technology and they have the industry that can consume these. For example, Japan, India, Korea, China. Whereas a country like Saudi Arabia or those some others who may not have that kind of technology to use them or the industrial applications, they will mainly be looking at these for exporting purpose. So that is where the difference comes as to where would they look, where would they use these materials. Whereas otherwise, the minerals are the same, the metals are the same that you get from deep sea resources. And yes, so they can be exploited from either way, either place.
Well, then let's go from there back to the India case, and maybe let's start with the question of what is India's need for establishing a deep sea mining industry at this point. I don't know how much you can talk about the geopolitical aspects, but just any insight into what's driving India in this space would be appreciated.
Yeah. Out of the three minerals that we spoke about, nickel, copper, and cobalt, India has nickel, but in grades which are very low. So mining it is becoming expensive and not to the quantity that we would like to have in future. Copper and cobalt are either not there or as good as not there. Cobalt is not there at all. Again, India is an industrialized country, as you know, and we are into all kinds of industrial products. So India's need is definitely there for these, whether it is for batteries or whether it is for any other applications. So India does need, like any developing country, and we have the industry that is there to consume, provided we have the proper grade available. Grade is the uh, content of a percentage of metal available in a mineral. That is one. Now, where does India stand? Uh, India already has now one site of 75,000 square kilometers to itself in the central Indian Ocean, which has metal reserves of 100 million tons, which is a very good quantity, and India can consume some of that. India can export some of that. We do have a processing industry also in India because we have lots of mines, which can probably, rather at the same time, we have also developed a process for three metal extraction from polymetallic nodules on a lab scale. It is established. So India is working towards. I mean, India knows where the deposits are. India has done, as we discussed, the environmental impact studies and the baseline environmental data collection, which is again going on. It's an ongoing thing. Processing technology, lab scale, is available in India and is frozen, and technology development is underway. So one of the institutes in India has already used or tried its mining machine at 5,200 meters depth in the central Indian Ocean last year or something like that, and for locomotion test. So locomotion test, then it will go to collection test, and then it will go to pumping test and things like that. So it is in. I mean, the process is on. Government of India for the last 40 odd years has been supporting this program, and that is how it has been running. There are designated separate institutions for each activity, whether it is exploration or EIA or mining technology or processing technology. For this purpose, different institutions that are responsible for these. That is where we stand. And more than that, now India also has signed contracts for 2 sites for polymetallic sulfides or hydrothermal sulfides, again in the Indian Ocean. So we have now 3 sites in the Indian Ocean.
And are these sites all in the area that is there beyond Indian extended economic zone? And is there also that's yes? So the sites you've been talking about right now are concessions under the ISA.
That's right. So these are all beyond the environment, the EEZ of India. At the same time, recently India did announce auctioning of some blocks within the Indian EEZ also. And I understand that the government is looking for parties that may be interested in further exploration of these blocks within the EEZ, provided they find partners.
Yeah, and that's kind of my next question is, to what extent is this being driven by government institutions in India, and to what extent is it private corporate actors?
As of now, it is 100% government sponsored programs and done through government supported or government funded institutions. Yes, all of these. So these are national institutions.
So when there's a test mining vehicle developed, that's being developed by a institution as funded by the government.
That's right. So the exploration and environmental studies work has been done by my institute, that is the National Institute of Oceanography. The mining technology development is being done by another institute, National Institute of Ocean Technology. Mine is National Institute of Oceanography. Then the metallurgical processing is being developed by another institute, which specializes in, which is called Institute for Metals and Minerals Technology. So, and all these belong to the government of India.
Is this common in Indian resource industry? Like on, say, land-based mining, is that often very government-driven, or is this deep-sea mining kind of a different model?
Yeah, so deep-sea mining is different. The all other mining enterprise in the country is, I would say, I would think that 60 to 70% is privately owned. Mining enterprise, and maybe 20 or 30% is owned by the government or comes under the public sector undertakings. So it is not the same as deep sea mining. Of course, the difference being that mining on land gives immediate profits. So the private enterprise has more interest, and has been active at it for ages.
Right.
I don't know, you might be aware that some of the Indian mining companies have bought mines in France and they are operating them. And in South Africa and in different parts of the world, Indian mining companies own companies all around the world. So yes, there are a lot of private operators in India for mining purpose.
Okay, but then you indicated that with the presumed opening that will be within the extended economic zone, now there's potentially the government is looking to collaborate with private enterprise to develop these. Did I read that right from you?
Yes, this is for the blocks within the EEZ that the government is looking for takers who would like to take up exploration on a larger scale and which can be converted into mining license later on. So what we call as the composite licensing scheme, and the blocks within the EEZ of India are now available for exploration come mining lease in future. You're right. Yes.
Interesting. Okay, well then, what do you have anything to say about what role India plays at the ISA negotiations?
Well, I have never been a part of the Indian delegation at the ISA annual meetings because I have mostly worked either as a researcher in my institute, providing data towards this, or after retirement as a independent consultant. So I've not attended the formal meetings of the ISA, but I've been to many workshops and training programs that ISA has organized as independent consultant. That's different. But then India has always been a member of the LTC, that is Legal and Technical Commission of ISA, which is the highest decision making body, and we always have a representation there, and we are always attending the council and assembly meetings of the ISA, which take place annually somewhere in July. So Indian delegation from the government of India side is always active in ISA, from what I gather from the information that we get. So yes, and more so, India is also a voice of the developing countries.
Yeah. Say more about that. This is something that I've kind of heard, and I feel like people conceptualize the deep sea mining tensions. Kind of there's the United States outside of the ISA. There's China is often put up as the enemy. Then there's the developing states, like you say, and it's interesting to hear how India fits into that.
Yeah, that's true. So I think India is probably a voice of the developing countries at the ISA, because not only because of the sheer size and the presence, but also because of the experience that we have gained over the last 40 years, having very actively been involved in different components of deep sea mining, exploration, technology, environment, processing, and all that. So I think that gives us a kind of leverage or a backing for getting into the negotiations with the information that we have already. I think so.
Let me ask you about your perception of the dialogue around deep sea mining, of the international debate. So you've been in this for a long time. I imagine that when you started, there wasn't very much attention on it. And at some point, the attention has ramped up. And I feel like I only kind of came late to this discussion. So I'm one of the people whose attention was brought to it only recently. But yeah, tell me your perception of the debate. And then I don't know if you want to wade in on kind of the more normative issue of should we or shouldn't we do deep sea mining.
Okay, so first let's talk about how it has evolved until where we are now, right? So in the 70s, 80s, and until the 90s, it was more concentrated on exploration only, whereas there were consortia that did build uh, mining systems, and they tested them between in 1970s. No doubt about that, they did. But then somehow that got wrapped up and didn't continue beyond that. So the initial phases were meant for exploration, I would say. And because the projection was that by the year 2000, mining should start. And so, I mean, that was based on the requirement of metals at that time, probably for defense purpose, because the world wars were going on or other things. I don't know the actual reason, but I've read somewhere. Subsequently, the countries which had started at that time, they tapered off their exploration programs because the date for actual mining kept on getting put off by a decade or so. Again, because of the lower requirement of these metals, or a lesser requirement of these metals in between the 1980s and the 2000. But then around 1990, again, the realization came up that at some point of time, mining might happen or will be required. So once again, the technology started getting developed, but again, mainly sponsored by the contractors. The contractors that by then had already signed contracts or were allotted contract areas, and so they wanted to proceed. In order to proceed further, they started building from a scratch a very small machine that could move on the seafloor and then collect and designing and all those things started somewhere in 1990s. Before that, it was mostly exploration. But then this changed, over a period of after the 2000, that there was a manifold increase in the number of contracts. Until the year 2000, there were only 7 pioneer investors who had been allotted those areas. But in 2001, when the contracts started getting signed between the contractors and the seabed authority, within those 1 or 2 decades, between, I think, until 2005 or so, there were hardly 8 or 10 contracts signed, whereas by 2020, there were 31 contracts signed. So there was a manifold increase in the number of contracts signed between different countries, sponsoring countries, and the International Seabed Authority. And that was again because of the realization that ultimately we will have to go to the sea to look for newer resources. And that is how, after the 2015 year mostly, the private enterprise also got into this. Many of them. Before that, it was just one. So many of them got into this of developing mining systems and marketing them for any contractors, because all contractors did not have the capability of making their own mining system. And that is where the private enterprise got into it, because they also realized that there was again a possibility of technology being developed and minerals being harvested from the seabed. So 2015 onwards, the impetus has been more on technology development. And 2020 onwards, rather 2015, once it was felt that technology development was going on at a promising scale, I would say, that the International Seabed Authority also realized that there need to be regulations put in place for mining. Until then, they had regulations only for exploration and for environmental work. So then 2015 onwards, the exercise to put in place what is broadly called as the mining code also started. So we have moved from exploration to mining technology to now regulation stage or policy making stage, where we are over these 40 odd years.
And what about the controversy and the polarization of the topic? Because that, I think, is very stand out to people who come to deep sea mining now, is that it's a kind of a famously polarized topic and only seems to be getting worse. And in fact, that's what I'm hoping to contribute with this podcast, is to try to lower the heat a little bit and lead to some more constructive conversation as opposed to polarized debate. But how do you see the influx of controversy and polarization into the debate? Was it polarized all along and that just ramped up, or did the polarization start at some point? How do you remember that?
Well, I would term it as not polarization, but an increased interest in deep sea mining activities, again coincided with the probably 2010, 2015, when the technology development on a larger scale started as compared to what was happening earlier. That when the possibility of actually mining these resources from the seabed in the coming 10, 20, 30 years looked like a possibility. I would say the more and more groups got interested in these, and which includes not only environmental groups, I would say even the financial institutions have got interested. Before 2010, 2015, there was hardly any information or interest, because it was just an exploration or a kind of research that was going on, which really didn't make any difference to anyone as far as the application or realization was concerned. So I would say that yes, there has been more interest, and which is expected, and I think quite normal to happen. So I would say that we have to think. I mean, if the question is DSM, deep sea mining, the right thing to do or not? Is that what we are talking about?
Well, I mean, what I'm interested in is I guess, do you see it as unnecessarily polarized, and why is it so polarized? And then, yeah, I would like to ask you that question: is deep sea mining the right thing to do? I guess I would ask if that's a good question, if that's the right question. But I'm certainly interested to hear your thoughts on it after so many years.
Yeah. Okay. So the first thing, you see, everyone in this world has a job to do. Okay. So don't take me otherwise, but I'm a geologist. My job is to look at the resources which can be useful for the mankind, for the humankind, right? And I do that job. An engineer, an ocean engineer, his job is, if assigned a project on making a deep sea mining system, he does that. A deep sea biologist has to look at what kind of life or environment exists in every part of the ocean. And if there is any human activity going to take place, then he needs to point out, or she needs to point out, as to what is the environment and what will be the kind of impact that will take place. So I would still define this as everyone's job that they are doing. And I don't see anything wrong in that, as long as these are not confrontationist. I mean, the ultimate aim of everyone is to look at the common good. Okay. So whether it is the geologist or the engineer or a policymaker or an environmental scientist, everyone's ultimate aim is to look at the common good of the world. Right. Now, considering that, we have to ask question to ourselves. Where are we going to look for the metals or the minerals that we need for the industrial growth that needs to go ahead if the future generations have to survive? It is that. And thinking in those terms, we need to find solutions around the problems that will arise as a result of this activity. For example, we build roads, we build bridges across bays, rivers. Isn't there an environmental impact, if that is the concern? There is. So do we stop doing that? Or we find a way to either minimize that or avoid it. Avoiding is never possible in any human developmental activity, because we have to be convinced that whether we need it or not is the question that we have to ask ourselves. Whether I can survive without a new laptop, a new mobile phone, or traveling in an aircraft, or having high-tech machines that need those metals, or I decide not to use any of those things in future and my future generations also will not use those. Or second option, look for new material which can replace these, with which I can make all those things that I'm going to need, either synthetically or naturally. Look for those materials. Just questioning an activity is not a solution. You have to look for something that will replace this so that this activity is not required. And the last option is recycling is also considered. But there are reports, and creditable reports, which also say that the quantity of recycled material can never match the demand which is going to increase from now. Whatsoever recycling method we may use, first of all, we do not have very efficient recycling methods. Even if we did have 100% of recycled material available, it cannot meet all the requirement of the world in the future. So we have these three options. One, not use any more resources that we are looking at. Second, find alternative materials. Third, use available material in the form that is available by recycling or by using it the way we can best make use of.
Well, I like your framing of we all have a job to do, and it kind of raises the question of whose job is it to make this tough decision about which of these. You've kind of laid out different options, and obviously it's not either or; it's a combination of all of them. And we, none of us needs another laptop. It's a question of how much we want one and what use we're going to make of it. So how do we make that decision? How does that decision get made? And maybe the question then is whose job is that?
Yeah, the best example here is oil reserves. Until about 60, 70 years before present, we drilled oil only from the continental areas, right? We have to answer the question to ourselves, why did we go offshore? It is obviously simply because the reserves available on land were not enough to meet the requirements. Although drilling oil at sea is much more expensive, much more difficult, technologically, environmentally, everything. But then we did go offshore and start drilling oil. It all depends on the need versus supply, or supply versus demand. That is the answer that we have to give ourselves. Whether I need or we need these resources for sustaining ourselves and the future generations, or we can manage with what we have. And if we did go, deep sea mining is similar to what we have done for oil and gas. And ultimately, we did go out to the sea just because there were not enough resources available on land, or this was the next best possible option that we took. Had we not done that, we would have been left with no oil reserves probably, Or, as I said earlier, look for alternative, such as electric vehicles or everything driven by electricity. Here is an alternative. If we want to develop electric vehicles or transition to greener energy options, whether it is solar or wind or others, you do need these metals. But we want to keep the temperature within 2 degrees centigrade of rising, which we cannot do with fossil fuels. So the option is again batteries or other alternative, transitioning to cleaner energy, for which these metals are required. So again, it's a decision that we need to make, whether we want to go towards in that direction or not. It's very simple, according to me.
So, in terms of doing this the best way we can, you've written a lot on techno-economic assessments, and I wonder what you see is the most important piece of technology that is either recently developed or not yet developed in order to make deep sea mining as, let's say, sustainable as possible. There's a word that has a lot of
Yes.
interlocking meanings. But how does the technology interlock with the sustainability, and what do you see as the most promising or necessary technologies?
Right. So yeah. So now we are talking how can we make best use of technology. As far as technology for deep sea mining is concerned, I divide it into three major components. One that is on the surface of the sea, that is a platform, a huge ship or a mining platform that will actually house all the equipment that will go down or work on the surface and do any pre-processing or storage and transportation, etc. That will be the support kind of platform. Second is the machine that will go all the way down and actually do the harvesting, which we call as the mining vehicle. So, and the third one is the connector between the two, that is called as the riser pipe. So when talking about this, the current thinking is that the mining platform is not going to be very difficult, because currently available platforms can be modified or remodeled into a mining platform with the available technology that is there. As you must have known, pre-prototype mining machines are being tested as of now, which will go on the seabed and pick up nodules. It is being done only for nodules as of now. Pick up nodules and put them into a hopper. The hopper, which will be connected to the conduit, that will bring it up through pressurized pumps. I think the most difficult part is the center part, that is connecting the collector machine, the mining machine, to the surface platform. And not that research has not gone into it, but that seems to be, to me, the most challenging part as far as deep sea mining technology development is concerned. Again, there are some companies that are now thinking of autonomous vehicles that will replace this center part and would operate from the surface platform, go all the way down, and they will have a payload capacity of a few thousand tons or so. They'll go and pick up whatever materials which is loosely available in the form of nodules, pick it up, put it into its container, basket or something, and bring it up all the way, so that we can avoid the center portion of the lifting pipes, because that is most difficult. One, because it will have number of pumps that should function synchronized with each other without even a single pump failing. Then there will be a lot of joints, which could sometimes lead to leakage or something like that. And then most importantly, there are cross-cutting currents that are all the way down in the water column. So it can twist and turn, or things can happen, and there can be breakage or something like that. So to my mind, that is the most difficult part that of technology that needs to be is being developed as of now, but in the process. And once all these three are integrated, or the center part is replaced with an autonomous vehicle which can operate on its own and come up and replace its batteries and discharge all the nodules and again go back and collect. Coming to how to make it sustainable, you see, a lot of environmental studies have now been conducted specifically for nodule mining by different contractors, where the environmental data, right from surface to water column to the seabed, has been collected as baseline information, which has gone into different databases and are being used for that will be used as the reference information when mining starts. But before that, there have been 5 experimental impact experiments. I mean, benthic impact experiments, including India has conducted one, Japan has conducted, Poland has conducted, NOAA has conducted, and there's one more. So, and Germany has conducted these tests where simulated mining was attempted to understand as to what can be the likely impacts. And those experimental mining results have been studied over different time periods, time spans, to also see how the recolonization or restoration of environment takes place on the seabed, which are actually in the potential mining areas. So these are not anywhere else. They are done within the so-called contract areas, right? Using this information, baseline, the impact from the experiments, and using them into models is giving us quite a good information from what we can understand as of now as to what can be the likely impacts of the large-scale commercial mining. Now, it may not be 100% correct or accurate. It could be 50% or 70% or 80%, but from zero, we have come up to some stage of understanding as to how the mining would impact the environment. So it's not as if nothing is being done. However, not just understanding of how the impact would take place, the understanding of that using models, but then a long list of mitigation measures have been brought out and shared with the technology partners to incorporate into the design and operation of a mining system in order to reduce the environmental impacts. There can never be zero environmental impact of any human activity. We just breathe out, we cause an environmental impact. We don't stop breathing, right? So we plant more trees. Anyway, so these mitigation measures, and they are there in my books and my papers, everywhere you will find them, which are being implemented by the mining technology developers to reduce environmental impacts. This includes...
I think it'd be really great to hear just a couple of examples of those, of places where the environmental study has led to some information about how to improve the mining system and how that improvement has been implemented. I think that would be interesting and helpful. If you've got any favorites that you would like to explain.
Well, I can talk at length about the experiment that I conducted, and I was responsible for planning that in the Indian Ocean. But then it was using an American machine, and the same machine was used by 4 different contractors in different areas for the similar kind of experiment that was done on a Russian ship by us also in the Indian Ocean, where we actually we called the word disturbed, and the machine was called a disturber.
Okay.
that's what it was meant for. This was as early as 1997. And we made the machine work on the seabed at 5 kilometers of depth for about 9 to 10 days over different intervals, and actually churned up a lot of sediment. Something like, if I'm not wrong, 580 tons of seafloor mud was churned up during these experiments over a distance of 88 kilometers. I mean, I think it's a huge disturbance that could be caused at those depths at that time. So these areas were then sampled for all environmental data, everything, before 1 year before for baseline data, just before the experiment started, whatever possible during the experiment was going on, wherein moorings, deep sea moorings were put to trap the sediment that was moving in different directions with current meters, so that we knew in which direction they moved and why. And then doing post mining, post disturbance studies to again collect information of what happens immediately after the experimental mining, 1 year after the experimental mining, 5 years after the experimental mining, 8 years after the experimental mining. So it was a long experiment that went on, even in our case, that was conducted. And we did find that, I mean, as expected, any disturbance that you cause is going to have the maximum impact immediately after that. And so there was churning of the sediment on the seabed. There was redistribution of the sediment on the seabed, everything that is expected to happen in the deep sea mining scenario also. Then there was a reduction in biomass. There were changes in physicochemical conditions. And it is undeniable, not unexpected. Over a period of time, we did realize by the 8th year of observation that we started doing, we realized that the baseline conditions had started setting in. Many of the organism species groups had got restored into the pre-disturbance levels. Not all. I know there is also study of 30 years post-experiment environmental assessment who have still found that the tracks are there even now. That is the German experiment which they had done. Because that is a physical disturbance that was conducted by digging into the seabed, which we did not do. But then they still find the tracks. So impact can never be neutralized immediately after. It takes time, but different parameters behave differently, which means restoration is possible. More than that, we also observed that every time we went to study, we also looked at the same parameters at the reference site. So mining site is where the experiment was conducted. Reference site is where we again studied all those parameters and also realized that the changes were not only due to mining, but also due to natural variability. And that is something that we normally don't think of. We just think that we create an impact and then we study the impact and then everything is washed off and this thing, that thing happens. But there are certain natural phenomena also that can cause larger or equally greater environmental impacts in the environment on the marine ecosystem that can sometimes wipe out certain species, which will again recolonize from the adjacent areas or over a period of time. That is a natural process.
So, what would be a trigger for such a natural disturbance? There
are underwater cyclones. It happens. There could be a volcanic eruption. underwater. That can happen. There can be a tectonic activity which will totally change the topography of the seabed with huge mudslides or huge movements on the seabed or anything like that. And those could sometimes, I have not measured them, but they could also be as huge as the impact that we might create, or maybe huger. Again, that doesn't mean to say that we should not think about the environment. But we need to have these things in mind, that there could be natural drivers that can change the environmental conditions in the seabed environment in any part of the ocean, irrespective of the human activity, which needs to be looked at and considered at some point of time.
And then what about the feedback from those studies into the technology development? Can you give some examples of technology that has responded to
Yes.
The science?
Yes. So, a few things that came out, which I call as mitigation measures to be incorporated into mining design, which is also there in my chapters. Some of them are common sense, that there should be minimum interaction of the mining body, mining machine, with the seabed, so that it doesn't actually, it reduces as much lesser the contact, that much lesser the impact. So if it could hover around, or if we could reduce the depth to which its traction wheels would dig in and things like that. So have a kind of a floating mechanism or a semi-floating mechanism, such that we touch the seafloor the least, and also pick only what we want instead of sweeping everything that is available. So selective mining, it is called, or strip mining or patch mining, which means you leave unmined areas in between the mining strips, so that the organisms from the unmined strips can come back and recolonize the mined areas, which happens. That happens on land also. So such areas get recolonized over a period of time if such patches or strips are left. And in case of nodules, what is more interesting is that nodules always have a patchy distribution, which means we may probably, for the sake of efficiency, in any case have to leave out certain patches. And there will be no 100% sweeping of an area to clear off everything from whatever is there. So either we deliberately leave patches or strips where recolonization can take place, or we may have to in any case leave those patches where the nodule abundance is lower, and the organisms living in that area can easily go and recolonize the mined areas. Now this is on the seabed. Again, our studies in the water column, and our meaning the world over, has also told us that there is something like an oxygen minimum zone about 1000 or 1200 meters from the surface in the water column, after which the life is minimum, which is a few very small percent as compared to the life in the above levels.
Mm-hmm.
Now when we do mining, we will bring whatever material comes from bottom and we will wash it out on the platform and release what we don't need, because we don't need to carry everything. It's an addition to transport cost and volumes, and then we don't know how to discard them on land. We don't want to bring what we don't need. So there could be some sediment, some muck, something sticking to the nodules, which can easily be washed off, and that needs to be released. So the best way is to either release that right at the bottom, so that we don't disturb the entire water column. So we have a pipe that goes all the way down, similar to a pipe that is coming up, and release at the bottom. Now, if technologically that is difficult because that can get entangled with the main pipe or something else or whatever. Then release whatever we don't need below the oxygen minimum zone, such that we save the life of the upper 1012 or 1200 meters, which is in much larger numbers as compared to the life below that. Again, it doesn't mean to say that we should not think about the life below that. I mean, no one's talking like that. But we have to understand, releasing anything at those depths is not going to settle down straight like a funnel. It's going to dissipate because of currents. So the concentration of the particles that are being called as the villains for the marine life in the water column will actually, the concentration will become so small because it is going to spread with the currents in different in certain directions, and depending on the size of the particle and the density of the particle have different settling rates.
Yeah.
It's not that it'll fall down as a lump, okay, which is, again, we are being told that this is going to happen and then everything is going to die. It is never going to happen like that, because we have the data for that, we have the understanding for that. And once these are implemented, there can be these mitigation measures incorporated into the operation of the mining system, that we can make it to the least the mining impacts. Does it make sense?
Yeah, absolutely. I want to be cognizant of your time here, Rahul, and maybe we'll wrap up on what you're currently up to at this stage in your career. But I guess before we go, is there anything else on the technology front that you would like to mention?
We have to employ the best available technology, and which can have the minimum impacts, so that technology does not become the cause against deep sea mining, if we consider that deep sea minerals are necessary.
Well, again, Rahul, thank you for making time for me today and for running through this rather long list of questions. Is there anything that we haven't covered that you think is crucial for people to know about deep sea mining before we wrap up?
Yeah, there are a few things that I would like to share, which I have kind of gathered over these years through my experience. It's like this, that we as a world community, and especially the next generation, which might see deep sea mining evolve over a period of time, needs to firstly not get carried away by certain propaganda which might come their way and which will actually influence our thinking. So, but our decisions should be more more logical, and more based on information. That is, we need to think, how do we develop in future? From where do we get the resources in future? And if we think that we do not need any more resources, then I take a decision today that I and my generations in future will not use any of the gadgets where those metals are used for which we will get from deep sea mining. So if we want to get influenced by someone telling me that 4 million square kilometers is going to be devastated because of deep sea mining, let me actually look at the reality. And I will tell you what the reality is. Putting together all the contract areas as of now, the 31 contract areas, the total area comes to about 1.45 million square kilometers, which is 0.45% of the entire area covered by all the oceans together. Less than 0.5% is what we are talking about as of today. Again, it is never going to happen that the entire 1.45 million square kilometers is going to be mined together, because it is practically impossible. Even if it happens, we will not have such a technology on such a large scale. Even if we had, we will flush the market with so much metal that the entire deep sea mining will go down. So it is, and calculations have shown, papers are there which say that not more than 10 to 20% of the entire area that is under contract will actually be mined. So 10 to 20% of 0.45% is what? 0.045%.
Mm-hmm.
Okay. So we have to keep the scale in mind. First point is we have to keep the need in mind. Second, we have to keep the scale in mind. Third, we have to keep the volumes of information that have been collected already and the efforts that are going into designing something sustainable. Because everyone is conscious of that, of the fact that we need to think about the environment and mine accordingly. But then, you see, every human activity is going to have some impact. So there has to be a balance that everybody talks about. How do we get a balance? Not by confronting each other, but by sitting together. There will be problems for any new development. As I said, you build a bridge, you build a road, you build an airport. Do we go and count the number of trees and the animals that live on those in the area where we are going to make these? Do we do that? And do we stop the project because of that? That is where the need comes. But then find out solutions such that we keep the impact to the minimum, and human mind is ingenious enough to find solutions to everything. And that is how we have evolved from where we were as cavemen until where we are today. We have evolved because of human mind. Today, blaming each other will not help. Think about it, whether we need something or not, and if we need, let's find solutions to the problems, is what I would say.
Okay, very well put. I think that's a great place to wrap up. Where just maybe as a closing question is, what are you up to now, and where can people follow you and keep up with your work?
Yeah, okay. Just a moment. This is my latest book, and this is the 5th one in the series of deep sea mining.
Deep sea mining management policy and regulation. And that came out this year, 2025?
Just last month. So yes, so it is in August or September 2025 that this book has come. So I've been writing these books now for the last 10 years. 5 books have come out, all on deep sea mining, different themes, each one containing sections which describe or have chapters by experts all around the world. So these are not written by me. These are experts all around the world who are working in different fields of exploration, of environment, of technology, of legal and economic aspects. Each book will have section based on the theme of the book, and there are chapters. On an average, there are 20 chapters per book by these experts from all around the world who have contributed. And these are actually the gist of what those people have done in the last 3 or 4 decades. You see, I am at a stage where now I'm close to retirement. But deep sea mining has not started. There are so many people like this who may just perish over a period of time, and a lot of information will go with them, or whatever they have published is scattered in different places. So the idea behind these books is to bring as much information as possible in these, which can be used as reference material for the future. And I am on my 6th book.
What is the next one going to be?
And that's on ocean governance for seabed resources.
Okay. Well, I guess that's a great place to point the listeners. I think that those books, I've used them. They're great for getting certainly an overview of all of the different topics published by Springer International, and so that's a good place to point people. You're on LinkedIn. I don't suppose you're active on any other social media?
No, that's it. LinkedIn.
Then I will.
Yes.
I will put links to those books and to your LinkedIn profile on the show notes. And I would just like to say thanks very much for your time, and thanks for all of your work on this topic. It's great to have somebody that's got such breadth of understanding, and thanks for making that available to me today.
Thank you very much. It was nice talking to you, and hope this podcast gives some useful information to the listeners. Thank you and bye.
Thanks for listening to the Elements of Deep Sea Mining. If you think this podcast is worth sharing, then please share it. If you have a moment, leave a rating or review. That would make me feel good, and it would help others to find the show. The views shared by the guest are their own and don't represent any official position or organization. You can find more episodes and show notes at elementspod.com, or drop me a line at eric@elementspod.com. I'm interested in feedback, corrections, and suggestions for future guests. Thanks for listening. See you next time.